Uh, Good afternoon, everyone. Sonal is present. Hello, Sonal. You got
Yeah.
connected? Yeah.
Yes.
Yeah. Okay. Good afternoon, everyone. Welcome to our second public lecture on importance of microfossils in addressing past climate change. Records from International Ocean Discovery Program. Uh, our speaker for today is Dr. Sonal Khanolkar. She is a postdoc and currently working with Department of Climate Geochemistry at Max Planck Institute for Chemistry, Germany. She has completed her master's from IIT Bombay, and then she continued her PhD from IIT Bombay itself. She has published more than 10 research papers in national and international journals. Uh, she was involved in the project like Ministry of Earth Science, International Ocean Discovery Program, Expedition 378, South Pacific, uh, Population.
350 or around 400. So what we are looking in the future is like really dangerous to us. So again, if we go back more in time and we look at now the really deeper time in the Cenozoic, which now spans the 65 million years ago, we produce now there is no ice old enough to hold the CO2 and to measure how the temperature. So now we rely on microfossils or to know about the climate change and to know about the temperatures or the CO2 levels. And these are all models, but the temperature changes are known through microfossils. So what we do now when we look at the sediment cores, which are drilled on along the oceans using this is a drilling ship which is famously known as the JOIDES resolution, and this operates all around the year for 40 years. It's been operating, and it drills cores in different parts of the ocean, and we drill different sediments of different ages, and we get continuous records of these sediments. So at some locations we may get it up to Miocene, some go from the Oligocene to up to Cretaceous, and thus we compile all these records together and then produce these kind of data. So these are marine cores, so they will have marine sediments and marine microfossils. So one of the microfossil group, which is the most abundant and also forms the major carbonate, is called as the single-celled organism called as foraminifera. So this is a foraminifera called Cibicides. It's a benthic foraminifera. And its record is, this species is there throughout the Cenozoic, and it's very commonly found or do the chemistry of the shells of these microfossils. You come up with the isotope ratios, which will help you in determining the temperature at which the ocean sediments were deposited, and thus the temperature of the seawater at which they were deposited, and thus we know some fair bit about what the climate is. Now, what is important to look at this graph is that, again, this is the projection that we have around 90 years from now, and it's about 900 ppm of CO2. But in the past, especially around the Paleocene, Eocene, we had very high temperatures and very high CO2 levels of around 1,000 to 3,000 ppm and very high sea surface temperatures as well. So what we are heading towards is towards back in the future, or it's around this level what we are achieving. So with the continuous increase of CO2 now. But what is important to know as a geologist is that it took 60 million years, of approximately 55, 60 million years to reduce the CO2, what it had achieved in that span of time to what it is now. But within a few lifetime or a human lifetime, we are increasing the CO2 to the same level. So that is the climate change at the rate at which it is happening now, and this is something of concern because environment takes a long time to stabilize, and we are just pumping in more of CO2. So, what is the importance of knowing about the climate change, and how are the microfossils playing an important role in addressing the past climates is what I will look at. So in this graph, there are two things. One is the age, and the next is the temperature that is plotted. So both of this, the age and the temperature, is known only through microfossils in sediments. And the first thing, as many of you must be knowing, is the geological timescale. And the entire of this Phanerozoic, which is 635 million years, is marked using the evolution and the extinction of fossil records, and that's how fossils are play a very important role in the construction of the geological timescale. So these are the divisions; these are the broad divisions of the geological timescale, and then we have the international chronostratigraphic charts, which are made and updated every few years, and we get better at telling time through the new discoveries. So then we subdivide each of these eras, periods, epochs into further stages, and if it gets even more at a higher resolution when you look at for example, these are all the planktic forams which are found in the ocean, and their first appearance and last appearance and of these individual species help in dividing the time scale into different zones. So these are different planktic foraminifera zones. And as a biostratigrapher, if you want to pursue this career, you would have to know the different kinds of forams, their taxonomy, and when did they evolve and when did they go extinct. And thus you divide this time scale into different biozonations, and thus you get better at telling time. It's like if you just say Oligocene, it's like a huge it's from 24 million years to 34 approximately. But then if you tell which species did you find, you get more higher resolution, maybe from 32 to 34 million years. So when you are on the drill ship and you are in these expeditions, what they expect from you is that when the drilling is going on, they give you the samples, and then you analyze the samples on the ship, and you look at these forams under the microscope and understand at what age in history are we. So that is the role as a micropaleontologist that you play, and that's the input that you give, and that's the most important input, because when you're drilling in the ocean, in the middle of the ocean, you want to know at what age have you reached, and is it the Oligocene, is it the Eocene, or is it the Cretaceous? So that's the first stage research that is the important research that goes on. And the next is obviously then you want to know now once you know that, okay, you are somewhere in the Eocene, so then you want to know what are the temperatures. And for them, again, the microfossils are useful. So you look at the shells of these foraminifera. They are made of calcium carbonate. And then you analyze these shells. So the second important part is, so this is another ship, and these are how the sediment cores are recovered. And then you sample them at intervals, and you process these samples, and you look at the various microfossils. So these are some of the planktics and benthic forams. This is under the SEM, and this is how it looks under the microscope. Some of these are nanoplanktons, diatoms, radiolarians. So the other microfossils like nanoplanktons and forams are made of calcium carbonate, but diatoms and radiolaria are made of silica. So most of our isotope work is done on calcium carbonate. So we mostly take the forams because they are, as you can see, the forams are around 200 to 400 micron size, while these are really small. These are like 2 micron size, and you can't separate them. So it's easier to separate foraminifera and to work on the chemistry of it. And most of these records, which are built of the temperatures, are using the foraminifera. So now those who don't know a bit about the isotope fractionation and how the temperatures are derived. So I have a small presentation for that as well. So this is a foraminifera shell. Now, this foraminifera shell, even though it doesn't really have the eyes and nose or whatever, but it is intelligent enough to attract the major ions, the oxygen, the calcium from the seawater, and form its shell. So it is like a powerhouse of all these oxygen, calcium, that it derives these minerals from the ocean in which it forms. And so now this is the foraminifera, and these are sort of the oxygen atoms. And there are two kinds of oxygen. I hope you know that one is oxygen, which is a lighter oxygen, which comprises of 8 protons and 8 neutrons, and it is oxygen 16. And the heavier one, which is the oxygen 18, which comprises of 8 protons and 10 neutrons. So this is sort of the heavy one, and these are the lighter ones, and they are happier. So this foram shell is made up of both of these oxygen atoms, the heavier one and the lighter one both. And so the lighter oxygen level, the water molecules which comprise of the lighter oxygen are sort of more. And these are the water molecules which comprise of the heavier oxygen atom, and the heavier ones are obviously a little sluggish. And when during evaporation, the lighter ones are preferred, and then they get transported they go gallivanting up in the clouds, and then they are precipitated as ice on the continents. And this happens, so you have like a lot of heavier oxygens are left behind, and the lighter oxygens are transformed when there is ice formation. So when you look at the ratio of 18 oxygen by 16 oxygen, it will be much more when there is ice formation on the continents, and when there is more, so when there is glaciation, there is the 18O by 16O will be higher, and when there is the warming or the formation of ice is not there in the continents, you know that the 18O by 16O will be less. So this is just a very pictorial description of how things will look at. So this is the foram shell, and the foram shell comprises of these oxygen atoms, and and it is in a ratio that which tells you about the temperature of the formation of the water using the 18 and 16 or measurements. So you take this foram shell and then you put this in the mass spectrometer, which gives you the isotope ratio of 18O by 16O, and thus you know the temperature at which that this shell was probably formed. So now you will say that why do we need it when we can really go and measure it now? So yes, today we can measure the temperatures, but when we look at past climate, which are millions of years back, we do not have any records of the ice or what was the temperature like. So these foram shells sort of record the temperature, and this is a logic that we use to understand the past climates using the foram shells and the calcium carbonate in it. So these foram shells are like deposited on the seafloor for millions, and then you go by the ship, and then you drill the ship, then you drill the core of the ocean floor, and this is the core that comes up, and you first you know the age using the different microfossils, as I told you, and it can really vary from how much you're drilling and what is the depth of which part of the ocean you're drilling and which sediments. So first, it is important to know the age using the various microfossils. And the second is that when you analyze these microfossils, they give you sort of the temperature changes which can happen, and then you record them. So this is just a pictorial description of how it happens. So this is one of the most famous records, and a compilation of the entire Cenozoic oxygen isotopes. And the oxygen isotopes are basically give you the temperature ranges. And as I said, so this is starting from around 56 million years right up to the present. And as you can see that the climate was very, very different. It went through a lot of changes. It was the highest temperatures were around the Paleocene-Eocene boundary, and it is known as the late Paleocene thermal maximum or Paleocene-Eocene thermal maximum. And this is what it is today. So the entire Earth history has gone through a lot of climatic changes, and we can know all of this only through studying microfossils and understanding the chemistry of it. So as I said, when the so this notation is known as the delta 18O, or so this is a measure of 18 by 16 oxygen. So as I said, 18 by 16 is less when it's warmer, and 18 by 16 is more when it's cooler. So there were no ice sheets which formed in from the entire Eocene almost. And at the late Eocene, there were the first ice sheets which were formed, and this is known as these are the Antarctic ice sheets which formed from the Oligocene, and we know it only because of the isotope that increased so much. The delta 18O increased that much. So, and then it has again, then there is a smaller glaciation in the middle, in the Miocene. This is the Miocene glaciation. There was Oligocene warming, and then again there was a glaciation. And so we know now we can predict the ice using the isotopes. We can predict climate change in the past, and that's the use or the beauty of these microfossils, and that they tell you not just about the climate today, but also about the climate of the past. So this compilation of these was not through only in one drilling site. It was a compilation of different drilling sites along different parts of the ocean, and the foraminifera called Cibicidus is used for the stable isotopes, and this diagram was formed, and it is also one of the highest cited articles in geology. So yes, this is like the most important part of the International Ocean Drilling Program. that was started 40 years back and much more before that, but these are the recent records. And okay, so now I will concentrate on this particular part of the curve when around the Paleocene, Eocene, and as this has the CO2 ppm, which may happen if we continue the same CO2 level is if the pollution continues and we have the similar CO2 level as that of the Paleocene, Eocene. So this part of the climate was the warmest in the Earth's history. That's a record that we have today. And so we'll look at this. So these are the Paleocene, Eocene boundary records. So we have a lot of records from the sea and a lot of terrestrial records as well. And as you can see, this is how the how the world looked like 55 million years back. It is not very different to what it is today. So we have it's not like it's not recognizable. So we have India, which was at the equator, and the North America, everything. The continents are sort of similar, but the climatic conditions were not. It was very, very different. And so how do we know about, first of all, yes, what happened was that there was a huge temperature rise in a very short interval of time. And this is only known through oxygen isotopes. But then you start looking at this, when you blow this small peak up, and this is what I'm going to do. If you blow this peak up in a smaller interval, this is how that peak looks like. So it is around 20,000 kiloyears. And within this 20,000 kiloyears, you have 20 kiloyears, you have a huge of oxygen isotope, decrease of oxygen isotopes, and decrease of delta 13C as well. So both of these indicate that there was a huge amount of warming, and this kind of warming happens if this kind of warming has to happen, you will have to burn the entire fossil fuels that are there in the world. And that's the amount of CO2 that you will have to generate to reach these kind of high temperature levels. So that was a lot of sudden amount of carbon that was released in the atmosphere during this particular period of time. And well, now you will say that, hey, there was no anthropogenic influence at that time, but there were other reasons because of which this carbon was released suddenly in the atmosphere. And even though this research has been going on for around 20 years, we are not very, very sure about the causes of what happened at that time. But we can just speculate. So just to give you an outlook of what happened in that period of time when there was a lot of warming, is that so this picture has been taken from the Dawn redwood forest of from the Axel Heidelberg Island in Canada. So in Canada, obviously, you know that the temperatures are very, very low. But what you found there was these stumps of the Dawn redwood forest, and these are huge, and it's forest. So and this is the kind of vegetation. The small yellow specks is the kind of vegetation that what grows now. So this is a huge difference. So this is the kind of fossils that were found in Canada 55 million years back when the climate was really warm. So we know that there was no ice on the poles at that time. So it was that warmer climate, and obviously the glaciation started around the Oligocene. That is when the ice started forming on the poles. So to reconstruct paleoclimate or climatic changes and what the world would have looked like, you have to look at different fossil records at different places, and then you sort of put it together. So you have to look at different locations at different latitudes as well, and hence all these kind of fossils will help you determine what kind of climate was there. So this is one of the major discoveries that, hey, there was no ice on the poles when the climate was that warm. And this is one of the future predictions that will happen, that the ice caps are going to melt if we increase the temperatures to what it was in the Eocene. So the other thing that we noticed in the ocean records around this Paleocene Eocene time was that there was a dissolution of deep ocean chalk. Chalk is carbonate. Okay, so chalk is another name for what we call the carbonates. So there was sudden dissolution at this Paleocene. This is the Paleocene-Eocene boundary, and at this juncture, that you will see that there is a reddish clay which is seen, and this is seen in around most of the other Paleocene-Eocene boundaries in the world, in the ocean records that you get from the drilling programs. And this is one way in which it is very much an indicator of the PETM as well. So this happened because there was this red clay which was getting deposited here, and there was no carbonate getting deposited in the oceans. So that happens when there is a lot of increase in pH and you dissolve and the carbonates, and thus there's no deposition of carbonates in the oceans. And this is what would obviously happen, and this led to the extinction of benthic foraminifera, because benthics are the one that are on the ocean floor and they dissolve. But the planktic forams also showed dissolution. However, they are the surface dwellers, the ocean surface dwellers, and they were still there. They did have some dissolution effect, but most of the benthics were gone. Benthic forams are not there around the Paleocene-Eocene boundary, and this is also called as the benthic extinction event at the Paleocene-Eocene boundary because of the increase in temperatures. So the Paleocene-Eocene thermal maximum is denoted by a global warming of 4 to 8 degrees Celsius of temperatures, and there is a dissolution of deep ocean chalk. The carbon isotope changes around 5 parts per 1,000, and the total duration was very short, 200 kiloyears. But what we are looking at right now, because of the anthropogenic influence, is like within few 100 years, we might reach these kind of levels. So the conclusion is that to achieve these kind of really warm temperatures, you need to burn a lot of fossil fuels, and that is like releasing 4,000 to 7,000 billion tons of carbon in a few millennia. So that can only happen if you burn all the fossil fuels that are there in the ocean today. So as I said, we don't know the actual reason for why this PETM or the sudden warming happened 56 million years ago. And even though there's a lot of research being done for the past 20 years since its discovery, we can just speculate on different types of sources of carbon which could have given rise to this kind of warming. One is the methane hydrates. I am not sure if all of you know about methane hydrates, but so the methane which is released by certain organisms on the seafloor at the poles are trapped in ice. And because of lower temperature and higher pressure, this methane cannot escape, and it's trapped in ice. And this is how methane hydrates are formed. So if you take the methane hydrates and burn it, it will directly burn like this. And they are the major source of carbon. So one postulation is that the methane hydrates were released in larger amount from these ice when these ice caps started melting, and there was sudden release of all of these methane hydrates, and that's how the CO2 was increased. The other thing is there were wildfires throughout the world, and or the wildfires or the forest fires. But then, if you have to really burn, you have to burn the wildfire, the forests, and the coals as well to release that amount of CO2 in the atmosphere. So this is one of the speculations. And the other is that there were intrusions, igneous intrusions into methane-bearing sediments, which obviously got burned. The thermogenic methane was released, and that caused the increase in CO2. So these are some of the speculations that happened, speculations which give you some indication of why the CO2 increased suddenly during the Paleocene-Eocene. So now that we have looked at the past, we would want to know what happens in the future. And this is like way ahead in the future. Okay, so these are just different models which predict that what happens if we suddenly dump in a lot of CO2 in the atmosphere now, like around 5,000 billion tons of carbon. If it is suddenly dumped in the atmosphere, to get it back to the normalcy or to the normal levels, first it will just shoot up, and then the CO2 will be around 2,500 ppm, which was the same as what it was in the Paleocene-Eocene. And then it will take a real long time, around 10,000 years, to bring it again back to normalcy. So what we are doing now is kind of reaching, we are already at 400 ppm, and if we continue this will just accelerate, and it will take thousands of years to bring the temperature back to normal. So this is one such model which shows that, and it's a compilation of different experiments. The other one is what they show, okay, the carbon emissions with 7 billion tons per year, but we have already crossed carbon emissions. We are more than 7 billion years. We are around 10 billion tons per year is the carbon emissions right now. So, but however, if the fossil fuel reservoir was 5,000 billion tons, and if we suddenly increase it, then there will be an increase of, this is 2020, so here we will be somewhere here. And if there is a sudden warming, there will be, and then it will continue for around the next 1,000 years. So it's important that we reduce the carbon footprint and the carbon emissions, and we are dangerously heading towards the state that we reached 56 million years back. So yes, obviously the ice at the poles is going to melt, and it's going to give rise to a very high sea level. This is just the prediction of what will happen at 5,000 years. The Greenland ice, if it melts, this is what Washington looks like when the sea level rises at 7.5 meters. So we are heading somewhere towards a disaster, and hope this sort of brings us to the fact that we should reduce our carbon footprints. So with that, I would give you some input of what I did this is the kind of work that we do in using the ocean cores, and we analyze the sediments, we analyze the fossils, microfossils, and they tell you about the temperatures, and they tell you about the kind of ecology, and the fossil records tell you about the kind of climate which was there millions of years back. And then, so these are some of the photographs that I've collected on my expedition, and will just tell you about the kind of work that happens. And some of you who are doing PhDs can also apply for these programs, as India is one of the participating country for this program, and it's quite prestigious. So we have, every expedition has at least one Indian scientist, and that's quite a good achievement, because India pays you and pays for this program so that we can participate. So I would suggest all of you to participate in this if you are interested. So this is what my drill site looked like. It was somewhere in the South Pacific Ocean, much south of the New Zealand. It's somewhere in the Campbell Island, and our main objective was the Paleogene. So it's from the Paleocene to Oligocene. So this is the interval that we drilled, and the main objective was to look at the climatic changes at a higher latitude, so somewhere really south, so somewhere near the Antarctic. What was the climate like in the entire Paleogene period? Were there warming? Was there a lot of? I mean, obviously there will be. When was the exact? And what was the amplitude of the warming in the poles? Was it similar to what it is in the tropics? Because obviously the tropics are much warmer than the poles. And so what did the the polar climate look like in the Eocene? Was one of our objectives. Then what kind of circulation patterns in the ocean were present during the Paleogene, because there is this Antarctic circumpolar current which is there now, but was that active during the Paleogene or not, is one of the questions that we tried and answered. I mean, we are still trying and answering, and we just got the course right now. So this research takes place around for a long period of time. So first is the identifying the correct site. So you have to, the co-chiefs already identify the drill sites, and then you participate in this program if you're selected. And then this is the ship, this is the drilling ship that we have, and it's a JOIDES resolution. It's like a floating laboratory. So you have a lot of instruments, you have mass spectrometers, you have microscopes, you have spectrometers, have the magnetometers, and all these kind of instruments. You get to know how the drilling takes place and how the science evolves in this. So this is a very good experience if you want to pursue research. And so this is the drill ship, and this is the rig. So this is the derrick or the drill rig. And okay, so when you reach the site, the ocean can be really quiet as the lake, and it can be really bad. So so this is the drill rig, and this is the drill floor. So these are all the drillers that they are mostly from Schlumberger, and they are the ones who actually drill the ocean floor. So we go to the site. Once you reach the site, then the ship has to be stabilized at a position. So and then the drilling goes on. You can't drill if the ocean is not quiet and it's rough. So it's important that you are lucky enough to get a calmer ocean, and then the drilling begins. So this is so these are the different drill bits, and so depending on the kind of sediments, we use different drill bits. This is the piston core, and the piston core is for the softer sediments. like chalk or calcium, if it's chalk, or which is made up of limestones, not the hard ones, the really soft limestones, then you can use the piston coring. If it's a hard rock, if you use a rotary drill, and these are the rotary cores for it. And it depends on the kind of lithology that you encounter. So this will fail at some point of time when you hit a hard rock, and then they switch to the rotary coring, and then once they recover the core, so this is the pipe in which they are recovering the core, and then it's passed on to the technicians. So these are the technicians who get the cores, and then the cores are first. There is a non-destructive measurements that happen when the core is brought down, and non-destructive means this core is intact and it's not cut into half. And so this core, it goes through density measurements and physical property measurements like magnetometers to understand magnetic susceptibility, to understand the density, the porosity. So all these non-destructive measurements are first done, and then the technicians will take it up and they will splice it into two. So one of this core, one of the half is for us to study and sample. The other half is archived and stored. So these are the working half is the ones that are marked with, I think, red. And so these are the different sedimentologists, and they are looking at. So we are not allowed to really touch the core right now, and they just take the smear slides and try and understand. They make the smear slides, and then they look at them under the microscope and try and understand the sediments in it. And then we are given, the micropaleontologists get the core catcher samples. The core catcher sample is that at the end of every core, there is some part of the core that is given to us to process and look at the microfossils in it. So this is the kind of sediment which is this is chalk, and or we call it calcareous ooze because it comprises entirely of nanoplanktons and foraminifera, which are made of calcium carbonate. So then you process these samples in the lab over there, and then you look at the microscope. Then you look at the different fossils, and then obviously you have to make the images and understand using taxonomy. You will have to identify the fossils and give the age to the sediments, and then you have to also make the reports over there. So then what we come up so my job as a micropaleontologist was to look at the forams, the planktic forams, and give the age zonations. So we try and understand each species and at what level of the at what depth of the core do we get that, and we give the age to the sediment cores, and that is your job. So there are different people who are working. Some are sedimentologists who look at the sediment structures in the core. Some of them are geochemists. So what they are doing, what she's doing right now is these are something called rhizon. So they suck the pore waters within the core. So this core is intact, but they just put a needle and suck the pore waters, and then this is a closer look of how it happens, and then they measure the chemistry of the pore waters in the different mass spectrometers or in their instruments, and this is so this is how the sedimentologist looks at a slide. He makes a smear slide of the cores and core samples, and then tells you about the core, how much is the calcite or fossils that he sees, or if there is quartz or if there are other minerals that he has seen. And you have to make a report of that, and everything goes in the report. So the other part of the important part is getting the magnetostratigraphy. So I hope you know that in this stratigraphic chart, there is always a column for polarity, if you see, or the crons. So it's always a chronostratigraphy, and this is the biostratigraphy that we give, and this is the chronostratigraphy, which is given by the paleomagnetists. And what they do is look at the susceptibility of magnetic materials in the cores, and they know that if there is they do their measurements and using a magnetometer, and they will tell you if there were reversals or normal periods in the crons. And basically, they are the ones who give this chronostratigraphy. So we compile both of this together to form the biostrat, and the chronostrat data goes together, and this is the magnetometer, and the core goes through this, and then the measurements happen. So basically, if you are doing paleomagnetism, if you're doing geophysical properties, if you are interested in sedimentology, fossils, or geochemistry, you can apply to these programs depending on your expertise. So as I said, the cores are split into half, and the working half is labeled as W, and it's stored in black caps, and the archive half is in the red caps. So then you store it back, and then from the ship they are transferred to these core repositories. So there are 3 main core repositories in the world where these cores are shipped to. One is in Texas A&M University, and the other is in Bremen in Germany, and the last one is in Kochi in Japan. So all these 3 repositories are the ones where all these thousands of cores which are drilled over the 40-50 years of drilling is stored. And you can always try, if you are not even participating in these expeditions, because not all nations participate, but even if you do not participate but want to work on this course for your PhD or for your research, you can always write a project, and you can submit the sample request to these repositories. And once it's approved, you will also get the samples from the age interval that you want to work on, and you can analyze the fossils. And that's how it is. So even if you do not participate, the IODP program is open for all, and you can still work on the samples which are stored over here. So thank you, and thank you for listening. And I would love to take questions if you have.
Yes. So anyone has question, you can drop down your question over the chat box. I will read the question, and Sonal will answer that.
Okay, I can't see.
Sonal, you can also see the
chat box. Okay.
Yes.
Okay.
Yeah. So there's a question from Dr. Sanjida Khan. You're working on foraminifera only, or any other microfossil?
I work on forams. No, nothing. I'm just working on forams. Yeah.
Okay. The next question is from Aisha. She's asking why we prefer foraminifera.
So it's not like a preference if you really love other microfossils like nanoplanktons or radiolaria. So we as a biostratigraphy team, we were like, so there were experts from not just not just to work on forams, but there were people who work on nanoplanktons, who work on radiolaria, and we need all of them because sometimes we do not get carbonate layers. So if we are in a really deeper bathymetry, so carbonate, I hope you know about the carbonate compensation depth, and below that you do not find any carbonates. So you find radiolaria or diatoms. So when you're drilling a depth which is really higher, you only find radiolaria or diatoms, and it's very so my expertise is going to fail in that. So you need someone who is an expertise in radiolarians or silicoflagellates or diatoms to work on it. Sometimes we don't find forams at all, but we find pollens or dinoflagellates. So it's totally up to you to which microfossil you like. But yes, the chemistry is mostly done. Like if you want to know about the temperature or the element composition or the seawater composition, forams are usually preferred because they are larger in size, they are easy to extract, and you can work on the shells of it very easily for the geochemistry. But apart from that, yeah, it totally depends on you if you want to what you want to work on.
The next question is from Saroj. Did the prehistoric mixing of the oceans, two layers, contribute to the Paleocene-Eocene thermal maximum?
Yeah, so it's a good question. Like if there is a lot of mixing, what happens? But then now we are very good at telling time because we are very good at knowing the taxonomic has been advanced so much that we know that if there is a mixing, there will be a mixing of fossils as well. So if there is a mixing of fossils, I know that certain fossils have got extinct at the Paleocene-Eocene boundary or have got extinct at late Paleocene. So it will not be there in the early Eocene sediments. And if they are there, then there is a mixing. So we try and drill continuous records, and we know that if there is mixing, we know it very well because there'll be a mixing of fossils, and but it can be recognized. So, but it's not because of the mixing that the ETM is there.
So the next question is from Shiva Teja. How will calculate the oxygen isotope analysis?
So that's done using the isotope ratio mass spectrometer. So you will have to study stable isotopes for that. I mean, I can't see the question. Where is?
Yeah, you can open the chat box.
Okay.
Could you see like there is a participants ka folder?
How will calculate oxygen isotope analysis? So this,
yes.
So this is done using isotope ratio mass spectrometers. And for that, you will have to, you really have to pursue that as a different, you have to be a geochemist and you will have to understand that. But if you are in India, I would suggest you pay a visit to Physical Research Laboratory in Ahmedabad, and they also have internships. So you can go and visit this and even get to perform some analysis as well.
So the next is kindly throw some light on thrust issue regarding paleoclimatology.
What is thrust issues? I don't know. So the important issues about paleoclimatology, there are no issues. I mean, it's paleoclimate, but I think it depends on your what you want to do and what you want to work in your research. So you can choose a time period, like for example, if you want to work on the Cretaceous Tertiary, the boundary where the dinosaurs went extinct, or if you want to work on the Paleocene-Eocene thermal maximum, so there are different periods of time where many major climatic changes have occurred, and if it depends, you have to choose one, and I mean you cannot do a research in your PhD on all the topics, but there are many intervals in the Earth's history where the temperatures were either very high or very low, or there were extinctions, so mass extinctions. So depends on you to work.
Okay, so now the next one is, how did the temperature subside after ETM?
I can't see that question. Okay. After the after the PTM or the ETM, there are many. So the entire early Eocene was a hothouse that we call, or a greenhouse period. The temperature subsided very gradually. We do not know how it subsided exactly, but it was brought to normal after a real long time to the formation of ice at the Eocene Oligocene boundary. So it took. I know that it took a real long time to reach the normal level. Yeah, but how did it subside is we do not know.
There are too many questions which is popping up. We will take like a few. The next one is, did the prehistoric mixing of the oceans two layers contribute to the Paleocene-Eocene thermal maximum?
No, there was no mixing of layers of any chance. I mean, if you mixing of layers, then you, that the fossils are also mixed. So you can avoid the sections where there is the mixing, and you have to look at records where there is the preservation is perfect and there is no mixing. I mean, if there is mixing, then we know it and we don't analyze those kind of cores.
Then the next one is, how can we compare ice core data with ocean sediment core data for carbon burial?
So the ice core data is only for the Pleistocene, and the ocean core data for the carbon burial. I did not understand this question.
Okay.
Yeah, maybe
we'll move to the next one then. If all the Earth's ice cap melts and flows into the ocean, what will happen to the Earth's rotation?
Oh my God! Okay, that's too much of a question. I do not know this, so I cannot tell you about the rotation of the Earth. Rotation of the Earth. No.
Okay, the next question is, ma'am, please tell us about carbon footprints.
Okay, the carbon footprint is how much amount of carbon you are consuming. So every day, if you are taking a bus, or it depends. If you are taking Ola or Uber, you have more carbon footprint because you are the only one who is traveling, right? And in the cab. But if you take a public transport, I think you reduce the carbon footprint. So that's like one of the best examples that this best is to walk or to cycle. But yeah, that's how you reduce the carbon footprint. So yeah, it depends on you.
So one of your junior from your same lab, she is asking question. Can you tell us a little on the del 13C curve and del 18 oxygen curve? How do they correlate? It's from Angana.
Oh, okay. So this one, right? So del 18O tells you about the temperature. So I can't hear it, Angana, but yeah, anyways. So del 18O is negative or is lower when the temperature is high, and that is because of the fractionation. And so the 18O in the 18 to 16 is measured, and 18 is the 16 is very high when there is a warming, and 18 is low. So that is how you know if that is a warming. And in terms of delta 13C is negative. So that means the 12C is higher. So 12C is the lighter carbon, which is preferred in mostly in plants. and it is preferred in biology. So I mean the 12C is tells you that there was a higher amount of photosynthetic activity, or there was higher amount of formation of this plants, and that's why it's so if there is a temperature increase and there's an increase in the amount of rainforest, so it sort of shows that. So there was a lot of carbon which was also 12C, which was getting consumed by the biological processes.
Okay, so the next question is, what is the impact of preservation state of microfossil for stable isotope study?
Yeah, that's a good question. So usually for stable isotope study, the preservation state always has to be pristine. It depends on what microfossils you're looking at. So mostly the planktics are not always very well preserved, but the benthics are really well preserved. The benthic forams are really well preserved. So the preservation state has to be really good, where the fossils have to be really, you can see the pores of the fossils. They are, when you do the SEM, you have to see that the pores are very clear, that they are not clogged, or there is not amount of diagenesis or diagenetic material on the fossils shells. So that's how you know the preservation state. So that can happen through SEM first, and then you do the stable isotopes.
Okay, the next question is, since microfossils help us study the past climate changes, does the study actually help us control the future climate change, or does it suggest that the change is inevitable? Also, can methane hydrate be used as an effective energy fuel with appropriate commercial production?
Yeah, methane hydrates are a very huge question, but methane hydrates are being explored. The problem with methane hydrates is that we don't know how to extract or control it. Like if you just even drill it, or I mean, you can blow up the ship, because it's that fast it can get ignited. So when the ship was in Arctic somewhere, I think we saw videos in which they had to really somehow they covered up the hole, and because they encountered some methane hydrates, and it can really lead to disasters. So we don't know how to yet explore. We know that they exist, but we don't know how to extract them yet. And what was the first part of the question? I think, how do you know if it can be used for the future?
Yeah, does the study actually help us control the future climatic change?
It doesn't help to control it, but it will help you know that what kind of scenarios are there in the future for you. Like there will be a lot of forest fires, there will be an increase in the sea levels, because there will be dissolution of the melting of the ice caps. So all these things are going to happen, and we know we can just predict it, but stopping it is not possible just by studying it. So we have to do it ourselves.
We'll take one or two more questions, and then we can stop, because there are plenty of questions. Are you ready to answer every question?
No, I think you can email me.
Yes, that would be better.
I think you can give my email ID to them, and then I can answer them.
Yeah.
Whenever on the weekend I will be free, so I can answer some of you for sure.
Okay, so let's go for the last question. How do you choose the locations of the boreholes?
Okay, that is done first through seismic surveys. So you have to have the seismics before drilling the site, and those kind of surveys are done by the co-chiefs. And also there are like previous records, if there are, of the previous drilling expeditions around the area, so you kind of know what sediments or what kind of a basin structure you're looking at. But it's very necessary to have the seismics because you don't know at some time what you are drilling, and it can be scary because during when we were drilling this particular location at some after a certain depth, we didn't have the seismics of the deeper levels, but what we encountered was there was a methane leak from somewhere, and that if that methane is very high, you can actually blow up the ship. So you have to be very, very careful, and these kind of surveys are done much before the expedition is they give you a green signal to that expedition.
Okay, Sonal, I think this we can ask the participants to email for further queries.
Yeah, I will. Should I just write down my email ID? Or?
Yeah, that would be great.
So I don't know. It's
you can add one. You can go to annotation actually.
Okay. I can't.
Okay, we will.
Okay, you can.
Yeah, with the certificate and the feedback form, which we will be mailing after a few minutes.
Okay.
And we will mail your email ID as well.
Okay, thank you.
Okay, so we are coming to the last session. I would request Dr. Nyanada Salvi for a vote of thanks.